this emission by the neutron star itself. This was by no means a one-man project, and in particular, I would like to thank Professor Stella, Professor Bacala, and many others, both in Palermo and in Rome, which have been invaluable during the development of this project and projects to come. Also, of course, I would like to thank you guys for this opportunity to present here and to see many known and unknown faces. So I'll just start now. So you've heard all about neutron stars yesterday, and I will not talk about them that much, but I will just try to remind you that the equation of state of neutron stars is, of course, one of the big open questions in astrophysics and in simply nuclear physics right now. And of course, the main problem is that we cannot measure directly pressure and density in neutron stars. But what we can do is we can measure, for example, for a certain neutron star, we can measure its mass and radius. And then from there, we go back to the equation of state, relationships. If we have, I don't know, like 3 or 4 measurements that are very precise of both mass and radius, we can finally say, okay, this is actually the proper equation of state to describe ultra-dense matter. But the problem is that right now we have very precise measurements of masses of neutron stars, even in the order of 1–2% of precision, but we lack precise measurements of radii. And this is unfortunately still true even to this day, that we have our best precision in these measurements is generally around 8–10%. To properly discover the equation of state of neutron stars, we will need a precision of at least, well, actually at most 5% on both mass and radii for many systems. So the method that we are trying now to, that I will explain to you and hopefully you will be convinced, is based on neutron stars that are within accreting systems. Now, in low mass X-ray binaries, a neutron star which is at the center of an accretion disk in which matter from the companion stars flows, these systems produce a wide variety of emission, and in particular, we've been studying the X-ray emission of these systems for at least 40 years now. And the emission that is coming from the disk, which is reprocessed by the very high energy emission, is basically divided in 3 components, which is a soft component reprocessing at very low energies, a Compton hump at the higher energies, and also this very broad, almost Gaussian profile at around 5 to 10 keV. Now, this was identified in the late 80s as the iron K alpha line, which is basically a simple fluorescence line of iron, which was broadened by relativistic effects given by the motion of the matter in the disk. Because, of course, if you have a rotating disk, which is going, let's say, in this way, then you'll have a certain portion of the disk which is coming your way, and you will see it as blue shifted, of course, the emission, and you will see the emission from the opposite side, which is red shifted. And you also have to add, of course, general relativity and everything to also account for gravitational redshift, which tells you that the emission in the middle is much more redshifted than the else. And what you obtain in the end is this kind of very broad and asymmetric profile, which is skewed, and it is very characteristic of accreting disk systems. In particular, these iron lines have been an invaluable tool for the study of these systems, because they provide information on the inclination of the system, they provide information on the inner disk radius of the system, and also in rotating black holes, they provide also information on the spin of the black hole. So, but these models had been worked out basically for black holes at the beginning. And what nobody had done before was consider that for neutron stars, you actually have a proper surface. You have a surface which will cut out some of the emission, because if the inclination is large enough and the inner disk of the radius goes close enough to the neutron star, you'll have that the surface itself of the neutron star will basically occult some of the occultation, because some of the points will emit, but the rays will impact on the surface before reaching the observer. And what you'll have is so that a certain portion, this kind of half moon here, crescent shaped, will be occulted to the observer by the neutron star itself. And this effect is only dependent on the ratio between the neutron star radius and its mass, because it's simply in terms of the gravitational radius of the star, so in terms of its mass. So what you can do is you can develop a code that tells you which areas of the disk will be occulted for a certain configuration. So for a certain pair of, I don't know, inner disk radii and inclinations, and of course neutron star radii. And you obtained that you can produce the shape, the proper shape of this occulted area, and you can see how this changes for different configurations. And of course, what you obtain is that you have that for larger neutron stars, here you can see we go from 6 Rg to 8 Rg of the neutron star radius, and for larger inclinations, going from 55 to 75, you obtain, of course, larger occulted areas, which is perfectly intuitive at this point. Now, when you know how to build these shapes, you can also define what will be the change in the iron profile that is produced by this area. And we developed a code that does that in Schwarzschild. It's very fast because it's basically all analytic, because we use an analytical approximation from the photon trajectories. And what you obtain is that you can study the profile and the differences between the occulted and unocculted case. Now you can see here in purple the occulted profiles. If the, for example, in this case, if the neutron star radius is of 6 Rg and the inclination is 75 degrees. And in green, the green dashed lines here instead tells you what is the profile for the same configuration, but without considering the occultation. And you can see that it's a pretty small difference, of course. In terms of the peak flux of this profile, you see we're in around 2 to 3% of the peak flux in difference. But, and this of course becomes larger and larger for larger neutron stars. This is going from 6 to 8 Rg. But the important fact is not the difference per se, it's the ratio between the two profiles. Because if it were just a simple difference along the whole profile, you would simply renormalize it while doing the analysis, and you would never know it's there. You would just think, oh, okay, this line is a little bit less bright than maybe I could expect, but you wouldn't know, of course. Instead, the ratio, here we can show the normalized ratio between the two profiles, has a very characteristic shape, which tells you that even normalizing for the loss in absolute flux, you would see this, this difference if you used a code that would not account for occultation. And so we're happy. We can say, okay, perfect. Now let's analyze some data and find out which is the proper equation of state of neutron stars. But of course, you haven't heard from anyone that we have found the equation of state of neutron stars. So you imagine there will be some roadblock here. And basically what we did is we found, for example, a good candidate, which is for U1636-53. It's a system whose inclination has been consistently reported to be very high, even in the range of 80-82, although there's still some uncertainty about it. The inner disk ratio has always been found to be very close to the ISCO, even reaching it at 6 Rg in some measurements. And it has a large flux with a very broad iron K alpha line, which can be properly seen here, for example, in this plot by Ludlam et al. So we analyzed new star observations of it, but unfortunately, we do not have the proper signal-to-noise ratio. Current instrumentation simply doesn't have the statistics to find such small variations of the flux and properly constrain the neutron star radius from it. So what we did is we turned our eyes to the future, and in particular, we did simulations with the EXTP instrumentation. EXTP is an X-ray satellite that will be launched hopefully in 2027, 2028. Every time I give this talk, they change the date, so I never know. But at this point, it should be 2027 or 2028 because the Chinese Academy of Sciences, which is the main operator behind this work, has already, well, greenlit everything and set out all the funds. So it should be this date. So by the end of the decade, we will have an instrument in orbit which will have an effective area 1 order of magnitude larger than anything we've ever launched. And 1 order of magnitude larger is large. It's actually enough to see the difference. Now, here you can see the simulated spectrum with the XTP using 1636, the same source as before, as a basis for the spectra. And you can see that if you take out the iron line, the whole iron line, the residuals are immense. The accuracy of this instrument will be extreme compared to what we have now. And if you instead turn on the iron line, which you should do, and just turn off the occultation while you're accounting for it in the analysis, you see that you will see some residuals. They're not as big, of course, as taking out an entire component, but this is actually seeable. This is actually something you can do data analysis with. And we simulated many of those configurations. And in particular, we simulated configurations ranging between 55 degrees of inclinations and 80 degrees of inclinations for 3 different neutron star radii to mass ratio. And we obtained that we can actually measure the neutron star radius in almost all cases, going from 55 to 80 degrees, with an accuracy that's always better than 5% in precision, always better than 5%, which is exactly what we need to pinpoint the proper equation of state of neutron stars. Not only we did that for simulations in which the neutron star radius is at the same radius of the ISCO, which is of course very positive for our sources, for our aims, but we also did it for simulations in which the inner disk radius is a bit larger than the neutron star radius, so that we can have, for example, some space for a hot corona or whatever you want to put there. And still, we find that in most cases, you can measure it. And in the cases in which you don't measure it, you still obtain a constraint, which is much tighter than the constraint given just by the best fit inner disk radius. So what this means is that translated on the radius to mass diagram that we were plotting before, if you obtain, for example, a measurement of a neutron star which has a radius to mass ratio of 6, you will obtain this green line here, and adding the 3% precision, which is the actually a little bit larger than the average precision that we find in our analysis, you will obtain this dashed lines, well, these dotted lines here. So if connected with other methods, such as the hotspot or thermonuclear explosions and bursts on the surface of the neutron star, this will allow us to pinpoint the proper location of the equation of state in the mass radius diagram for neutron stars. So we are very confident that when new instrumentation such as the XTP or even Athena will come out in the future, this method will allow us to, together with other methods that will be made available, actually pinpoint and constrain properly the neutron star equation of state. Now, just to summarize, iron line profiles have been an unique tool to study matter in the strong gravity regime, and in particular in accretion disk around contact objects. We developed a new model which is called shed disk, and this can fit in the Schwarzschild metric the emission for any given iron line that is occulted by a central body. Now, this body can be the neutron star surface, but actually, if you think large enough, you can think of optically thick coronae, both around neutron stars and black holes, which are actually a very important component of some models in well, right now. And with our model, we found that we can actually measure the neutron star radius to mass ratio with the precision that is required to put strong constraints on the equation of state. And actually, we also developed a convolution version of this model, which is, which makes sense because, of course, you would want to apply the same effect and the same occultation on all the components of the spectrum that come from the accretion disk. But unfortunately, while we were doing that, we discovered that many convolution models and the basic convolution routines used within XPEC, which is the most used X-ray analysis program in right now, introduce spurious effects on the broadened profiles. So we are kind of cautious right now in using convolution models freely, let's say. This is all, and thank you very much for listening. I can't hear you.
Thank you very much. How do you hear me? Yeah. Questions? I have one question, if I can. When you are calculating this iron line profiles, you assume that like the iron line is everywhere the same?
Yes, this is of course an approximation that the iron line would be everywhere the same, and this is why we have developed a convolution model, because we said, okay, if we want to have a series of iron lines, let's say, or a blending of iron lines that come from different parts of the disk with different ionizations, of course, you would have to account for that. Now, you can add, in principle at least, you can add like, I don't know, 15 iron lines and then let them blend, but it doesn't make, of course, the same, it doesn't have the same efficiency. The problem is, as I was saying, this convolution spurious effects that we found in XPEC's routines themselves is as large as 5%. So in some points is even 10% of the flux. So it's really something that we have been tiptoeing about all year, basically. But even talking with Keith Arnaud at the XPEC, which is who's one of the main programmer of XPEC, we couldn't find a solution. And for this reason, unfortunately, I have no solution for that except to say, okay, maybe let's put 15 different shapes and find which is the proper ionization or whatever. But this is the state of the models, unfortunately.
Okay, thank you very much. Other questions? Okay, so if not, thank you again.
Thank you.